Today, we will be exploring reverse engineering and quality control using FTIR, an absolute staple in the modern laboratory. My name is Lauren Armstrong. I'm the marketing director for quantum analytics, and I'll be your moderator for today's event. I want to give a quick note about quantum analytics. We are a value-added distributor of analytical instrumentation, specializing in chromatography, elemental analysis, and molecular spectroscopy applications. Tom, you could advance to the next slide if you could. We extend the value of the solutions we distribute by offering technical services, installation, training, and product support. Quantum Analytics is proud to be a distribution partner for the Bruker Optics organization, which means our clients can now purchase Bruker's portfolio of infrared, near-infrared, and Raman spectroscopy products directly from Quantum Analytics. We are super excited about that. Which brings me to our webinar presenter, Dr. Tom Tagg, Applications Manager for Bruker Optics. Dr. Tagg is a member of the Visiting Advisory Committee of the Metropolitan Museum of Art in New York and on the Strategic Advisory Board of Amplified Sciences. He received his PhD from the University of Utah in physical chemistry and a Bachelor of Science in Chemistry from the University of Texas at San Antonio. He is a member of the American Chemical Society for Applied Spectroscopy, American Physical Society, and the Optical Society of America. So this guy knows what he's talking about.
Well, thank you, Lauren. That's quite an introduction. So hopefully I can live up to those kind words. So I'm glad that you could join us today for reverse engineering and quality control via FTIR. And this is really a modern lab technique. And a key element. So when you look at the modern analytical lab, and Lauren gave an overview of some of the products that quantum analytical offers as well. So XRF, infrared spectroscopy, chromatography, and so forth. Where does infrared fit into that? And I would say even molecular spectroscopy, where does that fit in? So the answer is at the front of the line. So when you look at all the tools in the toolbox, from mass spectrometry to XRD, XRF, NMR, mass spec, whatever you're looking at, they may alter the sample to some degree or make it difficult to present the sample for another technique in the analysis chain. So for infrared spectroscopy, it's what I call a front of the line technique, where it's non-invasive, non-destructive. So then we think, what is added by using infrared spectroscopy? And the answer is specificity. There is no more technique, no more valuable or important technique you can use that gives you very specific information. The reason for that is every molecule has its own fingerprint signature in the middle infrared region of the spectrum. And that leads us to okay, now we know we want to employ infrared spectroscopy. And the focus of this webinar is looking at reverse engineering. So why reverse engineer a product or an object? So as Lauren stated, I am involved with analyzing art objects directly and indirectly, and in many other fields of study as well. So the bottom or common denominator really is looking at how molecules interact with light. That's what a molecular spectroscopist does. We look at how molecules interact with light. And so when you look at the development process in an industrial world, it can be very expensive to develop a product, or even to revise a product to be more competitive in the marketplace. It's expensive and can be extremely time consuming. I've been there. I've been a product manager in a couple of development cycles that took more than 4 years. So if you can reverse engineer something, you can cut that time down to a small fraction of that. And again, in a competitive market, that window of opportunity, so to speak, it can be narrow. And so you need to get your product with whatever revisions need to be done right to market as quickly and easily as possible. So if you look at a product life cycle, in most fields, a product is good for at least 10 years, sometimes less, sometimes more, but that's a good rule of thumb when you look at product development. So if your window of opportunity is 6 or 7 or 8 years, where your peak efficiency in sales would be, you want to match that by getting to market at the right time. So the obvious solution in keeping up in that competitive marketplace is to acquire products in question that may have attributes or qualities that are attractive for you in the development process, and then to disassemble them and analyze them. This reverse engineering process can really cut huge amounts of time off this process. So as we go forward, and you remember the title of the talk, there are quality control benefits to this process also. And as Lauren said, I'm on the advisory committee at the Metropolitan Museum in New York. And one of the things that we're most interested in looking at when we look at our objects is to figure out what was used by the artist, and so that we can best conserve and maintain the integrity of those amazing objects. So we're reverse engineering those as well. And it could be argued that even in at a crime scene in a forensics investigation where a suspect may have thrown their drugs in the toilet in a baggie, that we want to kind of so-called reverse engineer that, be able to figure out what is in the bag without opening the bag or breaking the chain of custody, so that when we go to court, there are no issues there with integrity of the evidence. So we want to be able to look in quality control and say, okay, there's a defect that doesn't belong there. There's an object, a foreign body that doesn't belong there. We want to analyze those contaminants as efficiently and as accurately as possible. They can really make a huge difference for quality issues. To say you make a food product or some other pharmaceutical product, and a customer complains, they say they broke a tooth on something hard in a food product. How do you analyze that? So you need to maintain a really good recording process, and we'll talk about that, and also work in a validated environment if at all possible when you do any of these analyses. So it's great for troubleshooting a manufacturing process. We have some problem, can we fix it? Troubleshooting that works great. Even looking at a part that may have failed in your production environment. Improving manufacturing efficiency. This is also an important concern. What can we do with the product? And I might argue that an analytical scientist has some advantages over a manufacturing engineer for being able to provide insight where some efficiencies can be had with respect to the manufacturing process by having that chemical understanding of the products that in question. And then I mentioned vibrational spectroscopy. Remember that we're looking at the chemical properties of the materials in question. So there are many tools out there for determining the physical properties. And indeed, in the examples we're going to look at, we're going to look at the optical microscopy, which also gives you more of the physical information. But when we look at the chemical properties, we're interested in looking at the how the molecules interact with light, how they absorb light or reflect the light. And we have some beautiful examples we'll go through together. Remember that it's very highly specific. There is no more specific tool you can use than vibrational spectroscopy to do the job. Non-destructive, it's low cost, and should be very easy to use. Just so that we know the difference between infrared and Raman spectroscopy. So infrared spectroscopy, we're looking at anti-symmetric modes of vibration. Okay, so let's talk about that for just a second. So if we consider a water molecule, which is H2O, it's a bent molecule. It has anti-symmetric modes of vibration because it has C2V symmetry. So it has a very strong infrared spectrum and is actually very, very weak in Raman. When we look at symmetric modes of vibration, like a benzene ring or something like that, we actually have a very strong Raman signal, and you can have a very weak IR signal in that case. So these are complementary techniques for analyzing materials. Again, for antisymmetric or asymmetric modes of vibration, we're looking at the IR being the best tool, and for Raman, we're going to we're going to look at symmetric modes of vibration. Raman has some advantages for looking at multi-layer films. I'm not going to get into that during this presentation, but I will show some beautiful examples of using infrared microscopy to analyze multi-layer films, and those work particularly well by Raman microscopy as well. So for infrared, just note that we're looking at fundamental modes of vibration. So these are the 0 to 1 or ground state to the first excited state vibration. And those transitions are most facile. So the intensity in the mid-infrared is strongest. When we look at overtone and combination bands where we're exciting up to higher order vibrational states, those transitions are less likely, statistically speaking, and are weaker. So the near infrared can be really useful for doing quantifications because those higher order transitions in the near infrared are weaker. You can integrate over more matter. So for quantifications, the near infrared is really many times superior to the mid infrared because particularly for inhomogeneous material, powders and such. But not as sensitive. So, and because you have many overtones and combinations rather than just one fundamental transition, specificity is not as good in the near infrared. So for identifying unknowns, the mid IR is best, and for doing quantifications, the near IR is best, unless the sample is exceedingly homogeneous, like analyzing a liquid. And remember that just stating what you all probably know, but we're going to send broadband light onto the molecules in question and excite the molecule vibrationally and see what light would be missing, and that's the absorption spectrum. When we look at a typical methylene functional group, you can see we have a symmetric stretch, an antisymmetric stretch, and then we have a rocking deformation and a scissoring deformation. So this functional group yields 4 bands in the middle infrared region of the electromagnetic spectrum. Again, let's talk about one last aspect of the theory before we start getting to some examples. So we're going to shine our light through the water molecules in this case, and some of the light would be absorbed or lost. One thing we have to be careful about in the infrared is because the absorption coefficients are so high for many materials in compounds in the mid-infrared, the sample has to be optically thin. So water in particular has one of the strongest absorption coefficients known in the middle infrared region of the spectrum. So you have to make sure water is thin if you're going to do it in transmission. 6 to 10 microns is all you can do. Otherwise you start saturating. Now, what does that mean? It means that the molecules in this case on the left actually are not seeing much of the incident light because the molecules before it in analyzing, being impinged upon by the infrared light, too much is absorbed. So that breaks down Beer's law also. So Beer's law only works if all the molecules in question have a fair chance, so to speak, at the incident light. So we need to make sure the sample is optically thin. For attenuated total reflectance, or ATR, that works great because the depth of penetration in ATR is typically only 2 microns. So ATR works the best, and transmission if the sample is thin. And remember that for the Raman effect, instead of sending broadband light through, we're going to send monochromatic light onto the sample, in this case a green laser, and we're going to look at what happens to the light. Most of the light would bounce, would go through and not interact with the molecule, and then light can bounce off elastically or inelastically. The inelastic bouncing generates the desired Raman spectrum. So we're going to look at a lot of examples today, or many examples, and let's talk about chemical imaging as well. So imaging is commonly performed now in many different fields in mass spec and NMR and infrared and Raman. So we're just going to go through the setup here. So for infrared imaging, every pixel of the chemical image is composed of an entire FTIR spectrum. So when you look at the image on the lower right, you can see I collected a 5 by 4 image of the sample in question, 20 focal plane array images, and each pane or of those 20 windows, so to speak, has 1,024 spectra there. So there are 20,000 spectra collected very quickly in literally less than a minute. It's just that efficient. So a focal plane array or a multi-pixeled array allows that to be done very well. I'm going through this pretty quickly, but a lot of detail went into the design and optimization of this infrared microscope called the Lumos 2 for doing spectroscopic imaging. And before we look at some examples, we have to understand resolution. So say we want to resolve features or contaminants or whatever, or layers in a multi-layer film, how small can we go? That's always the question of interest. Well, as it turns out, the Nyquist theory applies here. So if you say, I want to resolve, say, 10 microns, and you only have a pixel or a point at every 10 microns as shown here in the top part of this figure, you can't resolve the edges of this pattern. But when you say, okay, now I have 1.5 pixels per resolution element, so I'm going to have a point every 7.5 microns, I'm good. And indeed, if you go to 2 pixels for each resolution element, you're good. So if you want to resolve 10 microns, you really should have 5 micron spatial resolution, or 5 microns per pixel to resolve that. And that 10 microns in the example I'm giving is not arbitrary. As it turns out, 10 microns equates to 1,000 wave numbers, which is the center area for doing careful analysis in the middle infrared, where what we call the fingerprint region. So that 10 microns is most important, and indeed with the Lumos 2, we've designed it so that the default is 5 microns per pixel. Now, say you don't have a focal plane array detector, you can still collect the points one by one, going from one point to the other consecutively. And with a good MCT detector, that will work okay. You can also use a DTGS detector in the system. The results are good, but not ideal. It's slower because you're doing 1 pixel at a time instead of 1,000 a shot. With the focal plane array, the data is much better, and I'll explain that. So why is it so much better? Well, the reason is that you're collecting all the data at once. That means that in this case, I'm going to take a snapshot like I would with my camera, you know, an iPhone camera or something like that, rather than rastering 1 pixel at a time. And if you want 10 micron spatial resolution when you map, you actually have to close the aperture down to 10 by 10, and you're throwing away almost all of the light. So when you look at the Lumos 2, for example, it's designed to be optimal for about open beam for about 100 microns area. So if you're going to aperture down to 10 microns, you're using 1/10 squared of the light, or 1/100th of the light. So the focal plane array detector configuration really is superior when you want to do chemical imaging. And in the end, you have both at your disposal, and again, you decide what works best. So the 1,000 spectra per second, the resolving power is really very good. If you look at a Rapiflex mass spectrometry system that our sister company offers, they can get down to this regime as well, and they're highly complementary in being able to solve problems in that range. The Lumos 2 also has perfect registration of the visible images with the chemical image. So remember, the visible images give you the physical information or properties of the sample, and the infrared image gives you the chemical information. So again, having perfect registration is important. And then sometimes you want to have some flexibility with doing different experiments. And in doing that, we have the ability to have up to 3 detectors on the Lumos 2. And this instrument was really designed from the ground up for doing the ATR experiment, including ATR imaging with really high efficiency. So if we look at the image here, this is looking at putting together a large image over this whole area, and this would be about 50,000 spectra in a very short period of time. It's just short of 1,000 spectra per second, and the signal to noise is thousands to 1 for each spectrum. And we'll take a look at some examples as we move along. One of the issues with doing focal plane array-based imaging is that you're dealing with many detectors, 1024 detectors. So how do you deal with that? Well, we have a new patent, we call it PermaSure, in doing calibration, active calibration on each pixel all the time. So if you look at the non-calibrated red lines in the graph, you can see that the wave number accuracy moves around as a function of the pixel, and with the PermaSure, it's dead on. So this is really important, and again, even for the most demanding applications, this is really vital. Why is wavelength precision so important? Say you're looking at a band shift that may happen due to polymorphic differences, looking at a reaction process, a degradation process, those band shifts of a fraction of a wave number can be very diagnostic. And so to have wavelength precision, better than 0.1 wave numbers is really, really important. So when you look at employing microscopy into infrared microscopy and infrared analysis into your lab, one of the questions will come up is this platform compliant? And the answer is sure. So it will fit into even the most demanding SOP that you might be using in a lab. So it's 21 CFR Part 11 compliant, it's GMP compliant, GLP compliant, and GCP compliant, even for good clinical practices. It has automated test routines, so you can focus on the analysis. The system will test itself. You don't need to intervene at all with doing the analysis, and then you just get the printouts. In my lab, what I like to do is just have them run automatically every morning. I generate the PQ results. I print them out automatically in PDF form and archive them. And so that's my preference, and many labs run that way. But of course, it can be configured to fit into your SOP that you might have in the lab. And there are many polymer products used in regulated environments, and it's a good time to talk about polymer products. About 95% of all things that are made across almost any platform contain polymers. So polymer science is the biggest field probably right now for generating analytical tools to work well in that environment. So let's look at a good example. So this is an infrared microanalysis of an elastomer. So this is something that's not supposed to be there, and so I just collect a quick spectrum of the blue covering, and then the white particle that's not supposed to be there. And then all I have to do is right-click in the software, and it tells me I have cellulose. This is a challenging example at first glance. Is now I want to look at a particle or contaminant in a multi-layer film. How can we do this? Well, there are many ways to try and do this. The easiest way I do it is I actually make what I call an X cut. So I can actually cut and then peel back the flap and collect a spectrum via micro ATR very quickly and very easily. You'll want to practice with this on the side. Some films are harder than others, and you actually want to go through the top film only, not all the way through. That doesn't really help you very much. But this is a good exercise, and if you've ever used these overhead slide projectors, films, and other thin films of that sort, they're great to practice with. Here's a polymer that's a hard polymer material. How do you get a good spectrum off of this? It's obviously too thick to do in transmission, so we'll actually look in reflection. So when we do that, we actually generate a derivatized spectrum because the refractive index is poorly behaved when we look at the reflectivity of these polymers that are greater than about 10% reflectant. The refractive index goes to -infinity to +infinity as we go through an absorption maximum. So how can we fix that? There's a function in the software that actually strips out the refractive index spectrum and gives a perfect absorption result. Now, say we have a large object, say a refrigerator or a large part, and you want to get a spectrum from it. You can't fit it on a small ATR accessory in the sample compartment or under the microscope. So how do you work with that? And so what I like to do is use sandpaper. So a few particles can be removed from the object to collect a really good quality diffuse reflectance spectrum. The background is collected from the sandpaper where there are no particles, and the spectrum is collected where there are particles. So here's what the sandpaper looks like without the particles. And then there's my colleague Peng taking a few particles off my car. Yeah, she was authorized to do that. And you can't even see where she took the particles off. And now you can see the visible image after she had taken a few of those particles off. And you can see there's hardly any particles taken there. I use polarized light a lot of times, and in this case, these particles kind of come alive under polarized light illumination. And you could see the slip agent was readily identified by collecting the diffuse reflectance spectrum. So while we're looking at something that's only 1% or 2% reflectant, you can really obtain a very, very good spectrum. So, and this is looking at the slip agent that is on most cars now. And I didn't know this at the time, that these clear coatings actually improve the gas mileage by about 1 mile per gallon. So they are important for these automobile manufacturers to achieve EPA requirements. And again, very easy if you want to analyze something, that a piece of desk or any large polymer material, you could go actually into the production lab. If you're not sure whether there's a coating on there or anything else, you just take a little piece of sandpaper. If there's a residual that you're not sure of, you just take just a little bit of silicon carbide. You can get this stuff from Home Depot or any place like that, and be able to do this experiment very well. So reflection absorption, some people call it transflection, is another really good example. So you have a reflected background, and then you're going to shine the light through the sample and bounce off the backing, and then look to see how the signal works. So now, you remember we talked about the sample having to be optically thin. Now the samples have to be twice thinner because you're going to bounce through twice. So, and if the samples are very thin, you might have to do them at grazing incidence. But the lumos is sensitive enough that if it's thicker than about 20 nanometers, you can do the job with the lumos. Here's a good example, a good training sample. You just take some good scissors, and with good scissors, you can get them from a company called 2spi.com, number 2spi.com. These scissors have cut through hundreds of cans and anything, and they're as sharp as they were on day one. They're very inexpensive. You can get other tools like speedles and titanium tweezers and other things there very nicely. No, I don't get a commission from 2spi.com. And so you just cut this can and then place it onto the stage, and there's an image of a beer can. And there's the liner. So we can see the polyester liner or the polyoxyphenylene lining that would correspond to doing that type of very simple reflection absorption experiment. This is one of my favorite examples. Now I have something that I want to look at. It's a very thin multi-layer sample, and you can get these clips at the same place I just mentioned, and then you just put clamp them with the clip, and then you can just drop the whole thing into a methacrylate. The benefit to doing it this way, rather than dropping the polymer or whatever multi-layer sample directly into the methacrylate, is that you know, many samples are porous, and so the methacrylate would bleed into the sample and would complicate the analysis. So I really like using these clips to do the mounting of my samples. And for most samples, these clips would just sit on the microscope stage anyway, and you don't even need to put them in a methacrylate unless you're archiving them like I usually do. This sample was provided by Heiko Corporation, formerly known as Jet Avion. And we were interested in looking at this, one of their competitors, and they said their competitors could make these paint layers that were more resilient than what they could make. And so under normal bright field illumination, I couldn't really see the layers very easily, but on the right, under cross-polarized light, I could see each of the layers very nicely. And then just by doing a quick ATR, I could see each of the 3 layers quickly and easily, and in literally 5 seconds, to get really perfect results. This is looking at a visual image of an unknown on a circuit board, and you can see that little black piece of schmutz there. And so I'm going to go ahead and make the ATR measurement. And you can see where I make the measurement. If I use higher pressure, there are three different pressure settings in there. You can leave a little dimple there. I actually like the dimple because I capture the visual image before and after. So if I end up in a court of law, and I have testified in those circumstances in the past, I can show without question where the analysis was done. And then this is the circuit board, the unknown matter, and the green area that was the normal area. And then I just hit the library search, and I have a polymerized resin there that wasn't really supposed to be there. Well, when you look at fibers that should not be around, how do you analyze those? So there are a lot of ways to do it. My favorite is to use a membrane. The reason is these membranes like PVDF or nitrocellulose or any of these others, they actually work as kind of microscopic Velcro. So you can they'll pick up the particles and fibers and not let go of them. And all you have to do for ATR is you make higher pressure, so you will leave an imprint, but you actually will press down the fiber into the filter and collect a beautiful spectrum. You just divide off the spectrum of the filter. And when you do that, rather than subtract, is you don't double the noise like you would when you do a subtraction. And you can see a beautiful cotton fiber reference, perfect match there. Now, another way to analyze particles, and this is, we introduced this about a year or so ago, is automatic targeting of particles. So now I can have particles and fibers that are present, and I'll use the visible image. The software uses the black and white image to enhance the contrast. And we'll actually look and say, okay, what's the minimum object size and the minimal spatial resolution we want? And then the software will automatically target what we have there. And then, and so let's look at a real world example. This is analyzing particles on a gold filter. And so there are many of them there. And so we're going to use 10 seconds per position. And then we can quickly and easily right-click on the resultant spectra and see again we have cellulose there. We can also see in another spot that we have wool, again a very nice match, and we also have talc. So 3 different items very quickly and easily. One of the features of the software that I really like is it's just super user-friendly. So I will either do a cluster analysis or a principal component analysis. We call it an evolving factor analysis on the resultant images, and then it will enable me to actually find all the unique things that are in the chemical map and image when I'm done. So that's it. So it doesn't get any easier than that. You just do it. It tells you how many components there are. You click on the high area for each component, and then right-click on it to do the identification. And then you can also render the images very nicely. This is an RGB image showing the mixture of inorganic or organic particles that are there. Just works quickly and easily. Many different beautiful ways to render the data and images in the software. Note that when you look at intensity of these images, you're actually looking at a relative distribution. If you want an absolute distribution, then you actually need to use a calibration set, which is fine. We have many customers, particularly in the geology community, and some in the polymer community that are looking at distribution to see how well things have been distributed across their product. And so you can do a quantification by anchoring with known concentrations. Say you have a lot of particles, or you're working in an environmental situation where you want to look at microplastics in the environment. So we have a couple of different platforms we use, that people that we partner with. One is called the Simple platform, and the other is Purency. This was more than 6 million spectra collected. So instead of targeting each of these particles independently, now we're just going to let the focal plane array-based system analyze them all and come back and tell us what we have. So this works very well. It determines the type of polymer and the size and mass of the polymer. Now, for particle counting, what areas are people doing this? So certainly for microplastics, and you can do this with IR or with Raman. Both have transitions that work good in that area. For pharmaceutical products, tablets, transdermal patches, again, those are polymer-based, nasal sprays, packaging and such. This can be really important for doing particle counting. For semiconductor and circuit board fabrication, I published a paper in Test and Measurement World several years ago using fluorescence illumination, where I could actually find the particles and then use infrared microscopy to actually identify them quickly and easily. In the textile community, they call it trash identification and quantification. USDA and others use this method and use focal plane array-based imaging to identify these things that don't belong in the cotton in particular, but others as well. Looking at contaminants, food contaminants and other contaminants in polymers as well. Chewing gums, chocolates, melamine contamination, both IR and Raman work really well. And even in biomedical industries, I spent a few years in my now somewhat distant past characterizing and counting RBCs, WBCs, yeast, and so forth. So again, those work fine using molecular spectroscopy also. So let's do a couple of fun multi-layer film analyses, and I'm going to give two good examples. One is using transmission, where I'm going to cut the polymer thin, and then the second will be ATR, where in that case I'll just stand it on end and cleave it, and I'll put it into a microvise, which I'll show you for doing the analysis. So this, for multi-layer packaging and such, this is critical. Many films get degraded with exposure to oxygen or ultraviolet light or other environmental factors, ozone. So this can be really important. And this is a big reverse engineering application. I'd say over the last 25 years that I've been providing support to customers analyzing things, reverse engineering polymer films is probably #1. And so this is really a relevant area. And so the design and fabrication of these polymer films can be complex and very, very costly to do yourself, figuring out which ones adhere well to others and so forth, where if you just look at them, away you go. So let's go to the first one. So we're going to look in transmission. We're going to use a diamond transmission cell. So you can see Pong is manipulating the sample there using a probe. And so we're just going to cut a little piece of it, and we're going to place it in between two windows in a compression cell. And how do you collect the background? You can collect the background through the open area, but you'll get some fringing or channeling there, or you can put a little salt crystal next to the sample in question and be able to do the analysis quickly and efficiently. And I actually do both. So I like the idea of using the open air, so I do get that fringing, and that I can actually calculate the thickness directly from that. And so I know how thick it is, again, Beer's law, and I can also use the salt crystal to give me the perfect looking spectrum shown below. Now, remember, how thin does your sample have to be when you're looking in transmission? So you can say, well, okay, I'm dealing with an optically thick sample, polymers, maybe I can go 20 to 40, 50 microns, and sometimes even thicker than that. But not really if you want to resolve thin layers, because you have to look at the cone of light. And you can see on the left, my sample is thin, it's about a micron. And on the right, it's several times that. I would actually be blurring the image by using this cone of light to go through the sample. How do you do this? This is one of my favorite things. I've trained many colleagues, and over the years, you can buy a microtome, expensive cryomicrotome or room temperature. Leica makes really good ones, or you can buy a box of glass slides. And so in this case, I have 2 slides. I have my polymer film in between, and I'm just going to use a microtome blade, and you can get them from VWR or wherever for about $50 a blade, and you'll just cleave them. And when you practice, you want to use ball parts francs first. They're fairly easy to work with, and you can practice cutting thin sections. And then when you've mastered that, then you can move to Saran wrap and practice with that as well. So here's a good example using the bright field image and the polarized light image below. And these samples were actually cut by one of our salespeople. I just was training them on how to do this. And so you can see the sample will be thin. You need to look through it. And many times it will curl also. And then you know you've got a really good result. So it just a real simple way to, and requires maybe 30 minutes of practice to be able to acquire the dexterity. But it's very nice. So here's a real world example. Here's a 7-layer polymer film, the polarized light image on the left and the bright field image on the right. You can see there are a lot of layers there. So let's look to see how the focal plane array image looked. So you can see on the left, I have a triplet of layers shown by the higher light and then other layers there. And then here is looking at the 1654 to 1800 band. You can see where it is and where it isn't. And then we can also look at the CH band here, and you can see we have a hole in that one area I've highlighted. And then here's the NH/OH integration region. Again, you can see the high point. And then there's layer 1, layer 2. Are they the same? No, they're not the same. So even though there's small differences, and you remember I stated that distribution can be important, you can see I have layer 1 and layer 2, and you can see that banded around 2954 is very different. And then I have the triplet polyamide layer. This is common. Polyethylene is also a common one that people will use many layers adhered together. And I have polyethylene and 2 layers of polyester. And so I wanted to show this example of a multi-layer sample. You can see I have a micro vise. I placed the chip in there. And I'm going to do this by micro ATR now. So the crystal comes out from the objective, goes down onto the sample, and makes the analysis quick and easy. You're doing the imaging through the crystal, so the image fidelity is perfect going through the objective. If I'm doing single point imaging, I can use the aperture and just form the aperture to each of the layers quickly and easily. And then when I get the results, I just right click, get the answer. There's 1, 2, 3, very quick and easy to do, to accurately do the identifications. You should note that it is worthwhile to have good databases. You can build the databases yourself of things that you manufacture in your own environment, or you can purchase them commercially pretty cost effectively compared to days gone by. And this is an example provided very recently by a colleague of mine, Eric Klein, and this is looking at a micro ATR. And you can see there are many good layers there, and just snapping the focal plane array based image, I can quickly see I have PET, polyurethane, polyamide, ethylene vinyl acetate, and another polyamide layer. Very cool. And then I can highlight each of the integrated regions here. I have the polyurethane shown above and the PET shown below. So just really wonderfully resolved, and you can see really high signal to noise. When we look at the quality of the images, I have the PET spectrum, the polyamide, the EVOH, and the polyurethane quickly and easily. And again, as I said, even though these are very thin layers down to 3 microns, the signal to noise is spectacular. And so you can also look at the distribution of an aramid, PTFE, and polyoxymethylene here of a composite material. And I have the aramid fibers in black. And then the false color plot of the UV active contamination is shown here in the yellow. So again, you can track defects and inclusions, contaminants, and inhomogeneities really effectively, and reveal the chemical composition by multi-layers and components as shown in transmission and ATR. And this is a good example. There's one kind of challenging sample that I like that kind of shows off how good the system is, and this is looking at surface area. So now I have some organic or inorganic coating. Can I know the thickness? And in actuality, you can, and you can look at the thickness distribution. So the layer thickness for this thin coating on a drill bit varied from 1.70 to 1.76 microns. And so if we're looking at lubricants on ball bearings and other things, these FTIR microscopy works exceedingly well. You'd say, well, ball bearings, those things are round, how the surface is not even flat. As it turns out, it's not a problem, because for a microscope, actually the ball bearing is flat for the field of view we're looking at. So this is really a spectacularly good example, and shows that you can tell the difference, of a few nanometers actually and characterize that reliably using the microscope. And then kind of summarizing again, why imaging versus mapping? Very short measurement times, 1,000 spectra per second approximately, better signal to noise because you're not throwing away light while you're masking down with an aperture, and the samples are perfectly registered, and again, with the optical images as well, very reproducible. And then kind of summarizing in total, reverse engineering is really best accomplished, I might argue, or at least first with infrared microscopy, and then you can move to other techniques, and remember it's non-destructive as well, and the nature of the material will always determine which analysis method is best or what sequence of them is best.